Back in 2016, when I started dedicating my evenings and weekends to learning how to code and do serious stats, I was a bit lost, to be honest. Where do I start? Which language do I pick? Why are all those languages just named with one single letter, like R or C? Then I found some stats classes by Justin Bois, and it was a tremendous help to get out of that wood. And yes, this was a pun. I really enjoyed Justin's teaching because he was making the assumptions explicit, and he also explained them, which was so much more satisfying to my nerdy brain, which always wonders why we're making this assumption and not that one. So of course, I'm thrilled to be hosting Justin on the show today. Justin is a teaching professor in the Division of Biology and Biological Engineering at Caltech, California, where he also did his PhD. Before that, he was a postdoc in biochemistry at UCLA, as well as the Max Planck Institute in Dresden, Germany. Most importantly, for the football fans, Justin is a goalkeeper. Actually, the day before recording, he saved 2 penalty kicks and even scored a goal. Yes. A big fan of Los Angeles Football Club, Justin is also a magic enthusiast. He is indeed a member of the Magic Castle. This is Learning Bayesian Statistics, episode 70, recorded September 2nd, 2022. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the podcast, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, supporting LBS on Patreon, unlocking Bayesian merch, everything is in there. That's learnbayesstats.com. If with all that info, a Bayesian model is still resisting you, or if you find my voice especially smooth and want me to come and teach Bayesian stats in your company, then reach out at alex.andorra@pymc-labs.io or book a call with me at learnbayesstats.com. Thanks a lot, folks, and best Bayesian wishes to you all.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men dropping placebo-controlled science like I'm Richard Feynman?
Justin Bois, welcome to Learning Bayesian Statistics.
Thank you. Happy to be here.
Yes, I am very happy to have you here because, well, you know that, but listeners do not. But you were actually one of the first people who introduced me back to statistics and programming in 2017 when I started my career shift. So it's awesome to have you here today.
I'm glad my stuff helped you get going. That's the point. That's the goal.
Yeah. That's really cool. And also I'm happy to have learned how you pronounce your last name. Because in French, you know that's a French name. I don't know if you have some French origin, but in French it means wood.
I know it's a French name, but it's actually, as far as I understand, my family's from northern Germany. And there's a name there that's spelled Beuss, and it's pronounced like in German you say Bois. And then it got anglicized, I think, when I moved to the US. But I was actually recently, just this past summer, in Lausanne, Switzerland, and there was a giant wood recycling bin with my name on it. It said BOIS. So I got my picture taken next to that. So yeah.
Yeah, Lausanne is in the French-speaking part of Switzerland.
That's right.
Cool. So we're starting already with the origin story. So I love that because it's actually always my first question. So how did you come to the stats and biology worlds, and how sinuous of a path was it?
Well, I think the path that I had toward really thinking carefully about statistical inference is a very common path among scientists, meaning scientists outside of data scientists and maybe also outside of really data-rich branches of sciences such as astronomy. So I studied chemical engineering as an undergraduate. It was a standard program. I didn't really do any undergrad research or anything. And I got into a little bit of statistics when I had a job at Kraft Foods after undergraduate, where I worked with a statistician on doing some predictive modeling about some food safety issues. And I thought it was interesting, but I was an engineer. I was making the product. I was implementing the stuff in the production facility. And the statistician kind of took care of everything else. I thought he was one of the coolest people in the company, but I didn't really, it didn't really hook me into really thinking about that. But I went and did a PhD, and my PhD really didn't involve really much experimentation at all. I was actually doing computational modeling of like how nucleic acids get their structure and shape and things. And it just didn't really involve analysis of much data. Then in my postdoctoral studies, in my postdoctoral work, I was working with some experimentalists who had some data sets, and they needed to do estimates of parameters based on some theoretical models that I had derived or worked on. And I had done some stuff in various lab classes and stuff, but it's your standard thing. It's like, ooh, I know how to do a curve fit, meaning I can, I guess in the Python way, I would do it scipy.optimize.curveFit, or in MATLAB, I could do a least squares or something like that. And I knew this idea of minimizing the sum of the square of the residuals, and that's going to get you a line that looks close to what your data points are. But the inference problems, the theoretical curves were actually a little bit, say, for some of them, there was no closed form solution. They were actually solutions to differential equations. And so the actual theoretical treatment I had was a little bit more complicated. And so I needed to start to think a little bit more carefully about exactly how we're going about estimating the parameters thereof, right? And so I kind of just started grabbing books, and I discovered quickly that I had no idea what I was doing. And actually, neither did anybody around me. And I don't mean that pejoratively. It's a very common thing among the scientists. A lot of people in the sciences that don't work as much with data. And perhaps it's less common now, but it's definitely more common then, 10, 15 years ago. And so I just kind of started looking into how we should actually think about the estimates of parameters given a data set. And really what happened was the problem became crystallized for me, the problem of parameter estimation. And I had never actually heard that phrase, parameter estimation. To me, it was find the best fit parameters. If your curve goes through your data point, that means that the theory that you derived is probably pretty good. And of course, I didn't think about what the word probably meant there. I only knew it colloquially, right? And so, because I was focused on deriving what the theory is. And of course, that's a whole hugely important part of the scientific enterprise. But once you get that theory derived, and to try to estimate the parameters that are present in that theory from measurement, that problem just became clear to me. Once I had a clear problem statement, then I was able to start to think about how to solve it. So the problem statement was, I have a theory that has a set of parameters. I want to try to figure out what the parameters are by taking some measurements and checking for one set of parameters, the measurements would be different. How do I find what parameters there are to give me the type of data that I observe? I intentionally just stated that awkwardly, because that awkwardness there sort of it's funny, it made it clear to me that the problem was unclear. and so that's what got me into a Bayesian mode of thinking, because it was hard for me to wrap my head around what it meant to do that thing that I've been doing all this time, this minimizing sum of squares of residuals and trying to find the best fit parameter. And, in retrospect now that I've actually, that I taught myself, because I didn't really ever have a course in statistical inference or anything like that. Say, okay, I was essentially doing a maximum likelihood estimation, which is a frequentist way of doing parameter estimation. And I hadn't actually thought about what that meant. I mean, I understand that now. We don't really need to talk about that since we're talking about Bayesian stuff now. But it was just harder for me to wrap my head around what that meant. And so I started reading about the Bayesian interpretation of probability. And it really just crystallized everything and made it clear. And then I could state the problem much more clearly. The problem was I was trying to find a posterior probability density function for these parameters given the data. And that was just so much clearly stated in a Bayesian framework. And then that kind of lit me on fire, because I was like, holy cow, this thing that we do so often in the scientific enterprise, I can actually state the question, right? And I just thought that was such a profound moment. And then I was kind of hooked from there on out. And I was constantly trying to improve how I thought about these things. And, Yeah, so I did a lot of reading. I realized I just talked a lot. You probably have some questions about some of the stuff I just said. So please.
Oh yeah, always. But I mean, that's good to have an overview like that. And so I guess that's also like, it sounds like you were introduced to Bayesian statistics at the same time as you were doing that deep dive into, wait, like, I'm not sure I understand what I'm using. Then, oh, actually, I don't understand anything. And then I have to learn about that. Well, it seems that you were also introduced to Bayesian stats at that same time. Is that right?
Yeah, I think so. And I think this is actually sort of a classic way in which scientists come up with what it is that they want to study. Because until you start poking around, you kind of don't really know where the holes in your knowledge are. And so what I saw was like just a giant hole in my knowledge and my toolbox. And I saw the hole and I said, all right, let's fill it. And so I just started feeling around on how to do that.
I see. And I'm also curious as to then what motivated you to dive into the Bayesian way of doing things.
I really do think it was the clarity. I think that arguing about like what interpretation of probability you want to use is not the most fruitful way to spend one's time. For me, it was just so much more intuitive. I felt like I could have this interpretation of probability that it's a quantification of the plausibility of a logical conjecture, of any logical conjecture, gave me sort of the flexibility where I could think about like a parameter of a theory that I had derived and what value that might have, that I could think about that probabilistically, directly. And that was just very much easier for me to understand. I looked at some books that took frequentist approaches and I would read them and I would read them again and then again. And yes, in the end, I understood something. And one should not shy away from a certain method or a field or anything just because it's hard, difficult to understand. I don't think you should do that. At the same time, though, the ease with which I could understand how the Bayesian parameter estimation problem was structured and how you were ascribing probability distributions to parameter values, the also very, very pleasing structure of the Bayesian problem, which is where you have a prior picture of what your parameter should look like, that is then updated by the measurements you make via the likelihood to give you the posterior. That was really pleasing to me because that was exactly how I was thinking about when I'm doing science, right? Like I have some rough idea of what I think the parameter might be, So for example, the first one that I was really working on was I was measuring dissociation constants between two proteins. And so what that means is inside cells and outside, actually, proteins are binding with other proteins all the time. And the binding interactions are just central to all kinds of like life. Let's put it that way. They're a huge, huge part of life. And a very common thing to do is as you start to look at new pieces of proteins, is you want to start to look at how they interact with others. And so I was looking at how these two specific proteins bound with each other. And I was working with an experimentalist. Her name is Amy Baracco. And she was doing some careful measurements of using a technique we won't go into. It was a biochemical technique. And she would get some data. And I needed to measure what the dissociation constant is. Dissociation constant tells you how tight, how strong do these two things bind to each other. And so biochemists have a pretty good idea what the dissociation constant value is going to be. They know that it's not going to be so strong that the force holding things together is stronger than the forces holding a nucleus together. They know that it's not like atomic energy level forces, right? They also know that so you have some prior knowledge on it, right? You have some idea what the energetics are. And then you update those with the measurements. And it just made the whole process of what she was doing as an experimentalist, what I was doing as her theoretical collaborator with her, it just made it so much clearer to me when I started learning about the Bayesian approach to parameter estimation. And I found that really exhilarating. Yeah.
Yeah. So I love the two dimensions of this approach, which is like, on one hand, you were really diving into the methods, basically, and like trying to understand how do I know what I know about that, basically? And so which reminds me of how Michael Betancourt, for instance, entered the field also. And on the other end, also a very practical approach of being like, well, it's just like makes more sense to me in my work, and like I can more easily relate it to what I'm doing, which is also a big component of how people end up doing Bayesian statistics. So I find that super interesting.
Yeah. Actually, I don't know if you went over his story, how he came to it when you had him on the podcast, but it's very similar. He was doing physics stuff, and he was like, "Wait, I need to figure out how to do this." And it was the same thing for me. I was like, "Wait, I don't know. I need to understand this." And and one of the things that really I found that came out very nicely from doing it is the idea of you can pretty clearly see if you have identifiability problems. And some of the experiments that I've seen, even like measuring things like dissociation constants, there are definitely identifiability problems that I think a lot in the community meaning the biochemistry community, is just completely unaware of. And it's because, if you're kind of taking the approach that you learn sort of by reading what other people did in papers throughout the years, which is here's the best fit parameter. Like I have seen papers where it's sort of like how-to guides on how to do a certain assay. And then they straight up tell you, they're like, oh yeah, you plug this into, I don't know, whatever software it is, and it's going to spit back at you this number, which is going to be your best fit parameter. And then that's what you report. They'll literally say this in like technique papers, which is really, a lot of times you can get away with that because, the exact value of the parameter is close to that. It's fine for your operational purposes. That's fine. But it can really bite you if you if you have something that's like, for example, not identifiable. And so where the parameter value could be anything. And you might be saying, based on your experiment can't resolve it. And you're saying to yourself, oh yeah, the association constant's 1 micromolar, and it could easily be 1 nanomolar, right? And it's just not going to be identifiable in your assay. And so I started to see all these real benefits of taking these approaches, and it made me, I don't know, I think it just made me a much better scientific thinker. And to me, that was just, as scientists, we're always trying to, we always think very deeply about our problems, and we're really trying to understand, in my case, the living world. And the way in which we do that is by performing experiments, right? And making measurements and exploring with our eyes, whether those eyes happen to be attached to microscopes or telescopes or whatever, we do this exploration, and that's the center part of it. But if we want to interpret, if we want to learn from what we observe, that's where this data analysis comes in. And to me, I just felt like as I was learning how to do Bayesian analysis, that this was something that was so central to the scientific method, to actually the doing of science, that I had overlooked up to that time. And that, I'm a career scientist at that point. Now I'm really a career educator of scientists, but then I was a career scientist. And it was like, to me, it was just like this big moment, because I felt that now I'm a much more complete scientist now that I have this. And yeah, man, it was one of those few weeks. I remember them very clearly. I was at UCLA, and I would go to the student center, and I would get a burrito, and I would sit at a table with the burrito, and I was reading Jaynes's book. I don't know if you're familiar with E.T. Jaynes, which is very much on the scientific philosophy side of things. And I would sit there, and it was almost like I was high, meaning not on drugs, but like, I just felt like I was exploring a whole realm of science in general. It was really, really exciting.
Yeah, no, I completely understand. Definitely have had and still have some of those moments from time to time. Yeah. Well, actually, you already talked a bit about that, but let's do a formal intro of what you're doing nowadays. So, can you tell listeners, basically define the work that you're doing nowadays and the topics that you are particularly interested in?
Yeah. So after I did that postdoc I mentioned at UCLA, I ended up coming to Caltech, which is really a place that I really love. It's where I did my PhD. Yeah, it's an institution that's just a wonderful place to be. You're just surrounded by brilliant people. And I got the opportunity to come back here, as at the time my title was lecturer. My title now is teaching professor, which I think is more descriptive of what I do. So I am now not so much a scientist. I do collaborate with scientists on various things, but I don't run my own research group. I am a teaching professor. So I teach a lot of courses. And the courses I teach, I'd say my students are roughly more or less 50-50 undergraduates and then graduate students, mostly in the life sciences. This is neuroscience. We have an option called computation and neural systems, biochemistry, biology, bioengineering. So it's mostly that sort of group of students. And sort of my mission here is really to really train them to be world-class scientists. And so my contributions to science now really come through training developing scientists. Okay, so I teach a lot of different classes at Caltech, mostly to life scientists. That's biologists, bioengineers. We have students in special options like biochemistry, molecular biophysics, computational neurosystems, neurobiology. So all these different majors, and I teach undergrad and graduate students in that, roughly 50-50 undergraduates and graduate students. And so I teach a lot of different classes, all with the aim of training basically developing scientists. And at the risk of being a little bit immodest about my institution, our students here are really spectacular. They're among the best in the world. And so it's really a privilege to be able to train people of that caliber. It's funny, I walk around this place and I'm teaching students and I know that most of them are a lot smarter than I am. And it's really real privilege and real fun. It's a real challenge. It's something that keeps my mind fresh and keeps me moving. And so I teach a lot of different classes. I think the one that your listeners are most interested in are a couple of classes I teach in data science type stuff. So I teach, it's like a 2-term course. So that would be a total of roughly 20 weeks combined. The first 10 weeks are really about things like exploratory data analysis, sort of data management, like how you keep track of files. Even, we do a lot of practical things, like even how do you open files of different formats and make informative graphics from them. And then we spend roughly the last half of that class, like 5 weeks, on some frequentist-based approaches to statistical inference. The second term is entirely a course on Bayesian inference. And so that's 10 weeks on Bayesian inference. And in both courses, they're really applied to problems that come about in biology. We work with real data sets, many of them from Caltech, many of them from outside Caltech, from different types of areas of biology. And so they really do inference on real data sets together. I do also teach courses. I teach, like this year, I'm teaching a course. I teach a freshman lab course in biology, which is really fun. I teach an electrical engineering lab course where they build biodevices, basically the things that are going to get you the measurements that you're then going to need to do the inference on. I teach a course in chemical kinetics and thermodynamics, which are important for the physical side of studying life. And I also teach a course, I co-teach a course with Michael Elowitz on biological circuit design. So we look at how hooking up different genes, different cells with each other can give rise to function that's greater than the sum of the parts. And so I teach a variety of things, but kind of central to all of them is you need to be able to use a computer to do calculation, and then especially on the data science side. And it turns out that actually the data science courses are actually my most heavily enrolled as well. There seems to be a lot of really demand for that. A lot of universities now have programs in data science, and they are having, certainly students in the physical sciences and social sciences as well, are learning things about statistical inference and that sort of stuff. I would say that a lot of the biology training is lagging a little bit on that on the undergrad level. I think that'll change in the next 5 or 10 years. But so there's a lot of grad students who really want that training. They know they need it. And so they take my courses.
Yeah. So many fascinating things. I have too many questions. But actually, if you can you take an example from your work, probably in biology, to illustrate how Bayesian stats are helpful there, and also what you do basically as a researcher in that field?
So the problems that I approach they're really about how do I best train a student so that they can tackle any of the problems that come at them. And that's really one of the things that I really do there.
Oh, well, that's perfect, because that's also the goal of the podcast, to be, how do you learn Bayesian stats? So yeah, for sure, talk about that. That's awesome.
Right. So it's important to choose a variety of data sets. And what I do is I actually have a few data sets that I really kind of keep coming back to help students learn how to do more and more maybe sophisticated things and inference problems with them. And maybe I'll talk to you about one of my favorite data sets that I use in my classes. And we do 4 or 5 different things with this one rather simple data set. Now, I know that many of your audience are not biologists, but the cool thing about this data set is that it's so simple and easy to set up that you can even understand if you're not a biologist. But here's a little biology so you understand where it comes from. So this was an experiment that was done in the lab of Joe Howard at the Max Planck Institute of Molecular Cell Biology and Genetics in Dresden in Germany. And the data were acquired by Melissa Gardner, who's now a professor at the University of Minnesota, and Maria Zonic, who's a professor at Vanderbilt University. And what they were interested in is there's, inside all your cells, or well, not all your cells, but inside many of your cells, there are these filaments. They're like proteins that are linked end to end, and they're called microtubules. And it turns out that microtubules, they don't just sit there as a filament. They're actually constantly growing and then shrinking. But the shrinking is actually kind of really a spectacular event. In fact, it has a name called catastrophe because they shrink incredibly fast. It's like they kind of just, they grow, and then boom, they're gone. And so here was a very simple problem that Maria and Melissa were trying to study, which is, okay, I'm going to have my microtubule grow, and then it's going to undergo catastrophe. What is the amount of time? How is the time it takes before it undergoes catastrophe distributed? Right? So we want to know something about the probability distributions of the time to catastrophe. Now, this sort of sounds like a failure analysis problem, kind of, right? Or it sounds like, well, the simplest model you might choose, and this is what I start with students, is, okay, let's model this catastrophe as a Poisson process, meaning that you don't know how long the thing's grown. There's no memory of how long it's been growing. It's a biochemical process that just can like randomly get triggered, and we'll model as a Poisson process, which would mean that the time to catastrophe is exponentially distributed. So now you're going to have an exponential likelihood. So basically what they measured was over and over again, they measured how long did it grow before it underwent catastrophe with these microtubules. And they recorded that. And so we would take that data set, and then I give it to the students. We start with that and we say, okay, we'll take it to be exponentially distributed. We have one parameter. The exponential distribution has a single parameter, the so-called rate parameter. And let's estimate that parameter as a Bayesian estimation problem. And so they worked that out. We also learned how to do things like posterior predictive checks. And this is where you basically look at, could the model parameterize by your posterior, where the parameters are drawn from the posterior distribution, can that generate the data set that you actually observed? And the answer is definitively no. And in fact, you see it right away if you just plot the ECDF of the microtubule catastrophe times. You see this inflection point, so you know it can't be a Poisson process. So now the students got to think, okay, so what are we going to do? We're going to have to come up with another model. And so one of the things I have them practice, I say, okay, well, let's look at an off-the-shelf distribution. Okay, the exponential distribution is a special case of a more flexible distribution called a gamma distribution. The gamma distribution says, okay, instead of the time between arrival of Poisson processes is exponentially distributed, but how much time does it take, say, for 2 Poisson processes to arrive? Well, that's gamma distributed, with one of its parameters being 2, the number of Poisson processes that had to arrive. And then, we'll discuss this with the student. We'll say, okay, as scientists, does this make sense? And it's like, well, no, because they have some biochemistry knowledge. And like, well, that really makes sense if you have like the same biochemical process has to happen to trigger catastrophe. But it's probably different processes. They probably have different rates. And I think there is a distribution. There is a name for a distribution, I forget, where it's like the amount of time it takes for, let's say, we have 3 Poisson processes that arrive, and they have to arrive in succession with rates beta 1, beta 2, and beta 3. Now, I forgot what the name is, because instead we say, all right, look, let's do the work of deriving what the distribution should be. What should be the likelihood? Let's derive it. And then they go through that exercise. And then they do parameter estimation on that model. And then we bring that into model assessment. We do all kinds of posterior predictive checks. We do model comparison. And so what I'm showing the students is like, look, with this very simple experiment, it's literally just a list of times that they had to wait before they observed a microtubule catastrophe on single microtubules. Very simple data set. There's actually a lot to think about with the modeling. Then of course I'll do things like I'll give them data sets that I know are not with models that I know are not identifiable. And they'll have to work through that, and they'll have to find the non-identifiabilities. But yeah, so when you ask like what problems I work on, for me as an instructor, it's about what problems can a student learn the best from? And in particular, I want those problems to sort of be at least in their general area of science, which would be biology or study of the living world.
Yeah, I love that, and I agree. Now that also I'm starting to teach more on my end, it's something that I discovered is really important. Like a good data set, when you find one, you're really happy. It's like...
That's true. I think it's important to, it's not just the data set that's important. You have to think about what is the model, what is the question, and especially for pedagogies, can the question be clear? One of the things that I think is challenging with how statistical inference is sort of maybe taught in the undergrad or sort of used, I think, in literature by people who aren't thinking carefully about the inference problems is it's used in a way where it's sort of like, here's an off-the-shelf thing with a name that I can use and report. And one of the things I think that's actually really detrimental. Really what you want to have is, you're a scientist, you have to think, what question do I want to ask? What question am I approaching? And then I want to design my experiment around that question. And the interpretation of the experiment really is often, it's done within that. So I have a colleague, Rob Phillips, and he's written several books, and one of his books, which is one of my favorite of all time, called Physical Biology of the Cell. And it might even be in the front matter, but at the latest, it's in the very first chapter. He and his co-authors say in that book, implicit in every quantitative measurement is a model. And, we can talk about non-parametric statistics, we can talk about all that, but I think as scientists, that is the case, because what we're trying to, is very often the case. So what we're trying to do is we're trying to understand something more general about nature, how nature works, right? And so we do that in the context of models. Your listeners have heard of maybe F equals ma, Newton's laws of motion. These are models where we make measurements, and that's how statistics began, right? It began with Gauss and Laplace measuring movements of Jupiter, right? And they're trying to say something more general about Newton's laws of gravity, right? You can make the measurements, but we actually understand why these things move the way they do because there's a model there. And so for me, when we're trying to teach people about statistical inference, the model side of it actually really does have to have, it's as important as the actual data, the measurements themselves.
Yeah. And it's really that idea of generative modeling and Bayesian workflow that we've talked about numerous times on this podcast, and already with Michael Betancourt on episode 6. So actually, I'll put the link in the show notes to that episode. Very glad that it's still up to date. And also the book that you just mentioned, I think we should put that in the show notes for listeners, because that's something they may be interested in, for sure.
Well, one of the things I'll just say briefly is that Mike Betancourt in particular, he looms large in my courses. He's been a really strong influence on me and on the way I think about Bayesian inference. And I think that his approaches to how Bayesian inference fits into the scientific enterprise are very clear and just extremely valuable. And so I think that his contributions should be lauded. He's great.
And what's the name of the book that you just mentioned?
It's called Physical Biology of the Cell, and it's by Rob Phillips, Julie Theriault, Yanne Kondev, and Hernan Garcia. And so, it's called Physical Biology of the Cell.
Yes. Physical Biology of the Cell. Perfect. Yeah. Rob Phillips. Indeed. Perfect. Yeah. I'll put that in the show notes.
Yeah, but I love that idea. In fact, I don't know who said it first, because I first heard it said by his co-author, Julie Theriault. But I don't know if Rob, it doesn't matter. They did it collectively, I'm sure. But this idea that implicit in every quantitative measurement is a model, I think is really important for somebody as a scientist to think about.
Yeah, no, exactly. And that's something I often tell people, especially when they are learning about priors, and they're like, oh, I don't know what to choose. Like, it's just so hard. Like, it's just, you use priors all the time. It's just like you forgot that you use them, but you use priors all the time. It's just like it's implicit, and here the Bayesian workflow makes it explicit. So it forces you to basically lay down your priors, but actually just think about that question, and you'll see that you have priors on that question. It's just that you didn't think about them.
Yeah. I think that one of the things about the Bayesian approach is that it's very intuitive. And I think that the way we think about probability, that we can ascribe it not just to random variables, but to any logical conjecture, really sort of matches our intuition. And what the prior does is it actually helps you realize, no, yeah, you do know something. Again, so Rob is also a heavy influence on me in a different way than Mike is, but Mike Betancourt. But Rob Phillips, one of the things that he pushes, and it's a course, and I actually taught a course with him a few years ago on this, is this idea of sort of order of magnitude thinking, that you actually know more about something than you think you do. And I actually kind of use some of this ideas behind order of magnitude thinking and how we actually come up with priors. I'll give you an example. And this is something that Rob and I do in our class. And I actually literally just did it last week at a high school. My brother's a high school principal, and I spoke at his school with students about science. And I did exactly this with high school students. So anybody can do this. And I just asked them a question. I said, how big is an E. coli cell? E. coli, they know what E. coli was. It's this bacterium that lives in human gut and in guts of most mammals. And I said, okay, so how big is an E. coli cell? How long is it? And they're like, I have no idea. And of course, my point is that they absolutely have an idea. And I said, all right, so what we're going to do is called the bet the farm approach. So there's a figure of speech in English called bet the farm. So when in the old days, actually for a lot of people today too, if you had a farm, that's kind of all you had. That was your sustenance. That's what gave you your food, but that's also what gave you your income. And so the farm is basically all you have. And so would you be willing to bet your farm on something? And so I'm a big fan of the Los Angeles Football Club. They're currently leading the Major League Soccer in the U.S. right now. They're top of the leaderboard. So I guess that's going to put a date on this podcast recording. But if you asked me if I was going to bet the farm if they would win the MLS, I would say no. I'm not willing to bet that much. I think they will, but I'm not going to bet the farm. Now, if you asked me, would I bet the farm that the sun is going to rise in the east tomorrow? There is a finite probability that it won't. It's exceedingly small, but I would bet the farm on that. And so I said to the students, I said, well, would you bet the farm that an E. coli cell is smaller than a kilometer? Like, oh yeah, sure, I would. I'm like, so then you know something. You know that it's not bigger than a kilometer, right? How about a meter? Okay, how about a centimeter? No. How about a millimeter? Remember, you can see a millimeter with your naked eye. No. Okay, so now we're actually getting down. And then I go to the other side. It's like, all right, is it bigger than an angstrom? That's about the distance between the hydrogen and the carbon in a bond. Well, of course, it's got to be bigger than that because it's full of molecules, right? And so you come from both sides with this order of magnitude. And then if you want to get an estimate for it, you just take the geometric mean of the two sides you come from, right? But you can also do that for setting priors. So if I'm going to make a measurement, so let's say I'm going to actually take measurements of the size of E. coli cells. I can do that with a microscope or something like that. Now, and I want to try to report what's the typical size of an E. coli cell. Well, my posterior is going to have a nice Gaussian distribution, probably something centered around 2 microns, because that's how big they are, 2 micrometers. But for my prior, this is a common technique that I like to use for that, is I do this bet the farm approach, and I get bounds on either end where I'm like, I would bet the farm that it's smaller than the big one or bigger than the small one. And then I'll essentially throw a log normal on it. You will say, okay, so log base 10 of this parameter is going to be normally distributed. And I'll say, okay, I'll leave, say, 5% of the mass, probability mass out beyond where I bet the farm. And now I got myself a nice prior. But the idea is that I asked these high school students, and I said, how big is an E. coli cell? And they said, I have no idea. And then instantly we were able to say, no, you do. You do have an idea, right? And so I do like that. I also think that we are naturally sort of programmed to think in a Bayesian framework. And this came clear to me about 7 years ago. So I live here near Pasadena, and we have there's a very nice garden called the Huntington Gardens in Pasadena. And if you're ever in the area, I'd recommend visiting it. And when my son was little, we used to like to go there early in the mornings on the weekends because little kids wake up at an unreasonable hour. And so it's a nice place to go out to the gardens and walk around. And so one Saturday, my son was 2, and it was the first time he used the word probably, right? It's the first time he used it. And so I had him, he was still in a diaper actually, and I had him on his changing table.
It was actually his first word.
Right. His first word.
No, the second word. The first word was bait.
That's right. Something like that. Anyway, so I had him up on his changing table, and I said to him, I said, hey, what are we going to do today? And he looked at me and he said, probably we're going to the Huntington. And I was just really struck by that. I was like, oh, wow, this kid's Bayesian. Because he was thinking about exactly that Saturday. He wasn't thinking about a very large number of repeats of that Saturday, right? No, he was thinking specifically about that day. And he was ascribing a probability to an event, a probability to a logical conjecture, which was not really a random variable. It's not something that could be repeated over and over again. It was that's going to vary from experiment to experiment. There's only one experiment. It's this day, right now. Yeah, and I was like, I think we're wired to think about probability in the Bayesian way. And that's the moment where it dawned on me. I'm like, this is why I understood what I was doing when I started reading the books about Bayesian approaches. Because apparently I'd been thinking that way, probably like him, since I was 2.
Yeah, I love that story. And I love also like your reaction when you hear your son saying probably. He's like, Bayesian.
Yeah, exactly. My wife, after I got him ready, I ran out and I told my wife that. I worry sometimes about my wife that she might damage the muscles in her eyes from rolling her eyes so much after I tell her things like this.
Yeah, I love that because I think most people would not notice the probably. You did.
Exactly.
You're Bayesian.
Right, that's right.
I'm so proud of you, my son.
Yeah. Yeah.
Well, actually, something I wanted to ask you, because you're very passionate about education and teaching science. So I'm wondering if there are most important skills that you're trying to instill in your students.
Wow. Okay. That's a good question. It's almost less of a skill. I answer this question, right? It's a mentality that actually requires some skills. Really, the mentality I want them to have is to not be looking to statistical inference for just like an off-the-shelf answer. This is a tendency, I think, for a lot, especially in biology. I have some friends in medicine, I have some friends who work in medical research, and like the FDA has specific things that you're supposed to do statistically with data as you're going through like clinical trials and these sort of things, where it's like, this is what I'm supposed to do, and then this is the answer that I get. And I think one of the things that I learned quite quickly as I started, especially getting into the Bayesian type of analysis, is that just doesn't fly. You need to think about your experiments as a generative process. You need to remember what Rob and Julie and coworkers and co-authors said, which is that implicit in every measurement is a model. And that model is different from measurement to measurement. You're studying different things, right? And you're studying them in different ways. You're making the measurements with different instruments. And what I want them to have is the mentality that just like you don't just do a standard experiment every time, you shouldn't be doing a standard analysis every time. Like you shouldn't just be looking for the quick thing that's going to tell you a yes or no, or that's going to give you a number and then you check to see how close to 0.05 it is. I want to break. And I do get a lot of students come in and say, how do I do this? I need to do this for my paper. My advisor wants this. And so to me, that's the big problem, because as I told you earlier, I discovered early on that the statistical inference process is an integral part of the scientific method. And just like you think carefully about an experiment, just like you make adjustments to experiments to get better measurements, to get different measurements, you need to adjust your analysis as well. The word that Mike Betancourt uses a lot is bespoke, which is kind of a fancy way of saying tailor-made. And I think that that's a great mentality. And so that's what I'm trying to get them to do. Now, to your question about skills, that's the number one thing. Now, the problem is that they won't do that if they're not able to, right? So you have to then give them the skills to be able to do that. And that is a real challenge, because you have to find the right balance of rigor and breadth of coverage to give them the toolbox they need with the understanding of the tools they need. When it's weird, statistical inference, you'd think it would be more mature, but it's just we're just not there, where there's a lot we just don't understand about how it works. And so that has always been a challenge for me. My course changes every year based on my understanding, based on what I think is going to be an easier way for them to grasp it, based on what I think relative importance of things are, and based on where the literature has moved. As statisticians, particularly applied statisticians, are learning new things. And so from the Bayesian inference point of view, what are the skills that students need to think generatively? The first thing that they need to be able to do is they need to be able to codify their domain knowledge into a likelihood, which means that they need to understand what probability distributions are, what probability is, and they need to take what that implicit model is. And they're the ones who know it the best. They're the ones who study E. coli, or they're the ones who study how muscles work, or a certain part of the brain, or olfaction, or whatever. They know it, right? And so you have to help them put that in the language of likelihood, right? From that, Bayes' theorem kind of, it structures itself, right? You put a prior on that, and now you're done. I always tell the students in like week 2 of my Bayesian class, I'm like, I'll write down a posterior, right? Because we'll specify a likelihood, and then we'll specify a prior. I'm like, oh, here's a posterior, it's done. And I'm like, oh, class ended early. We don't have to do the final 8 weeks. So everything else after constructing the posterior is making sense of it. And so constructing the posterior takes a lot of domain knowledge, which means, to come up with the likelihood and the prior. But then it's all about making sense of it. And what skills do you need to do that? For me, the big one is really just to be able to sample out of a posterior distribution. And, we can talk a lot about the theoretical underpinnings of all this stuff, including how samplers work. I touched on that briefly, but ultimately you can't have a full bulletproof understanding of everything that you're doing, partly because people who are experts in this don't have it. And so, I really focus on, okay, how can we do sampling? How can we make sure that our sampler is working as it should? How can we identify potential issues with inference that we can get from our model? One of the things that, I often remind students of is that, I give them a problem that's not identifiable. And the model that I give them is very well rooted in physical theory. Like, it's using tried and true laws of thermodynamics. And it's important for them to recognize, oh, wait, I shouldn't be adjusting my model so that I can get it to be identifiable. Yeah, there are some things you can do with priors and things like that if your prior's way off or something. But fundamentally, this problem I give them, there's just no way you can get a couple of the parameters. And it's because the experiment can't resolve it. You don't want to start contorting your model to your experiment, because then your model's like, your model should be informing how you do your experiment. And if a parameter is simply not something you can identify through an experimental method you're doing, you have to think of a different experiment to get at that parameter, right? And so all those things, the skills that you need to do that, I think, are understanding probability and probability distributions so that you can construct the model. And then secondly is to be good samplers. That's really what my course is. It's like model building and sampling and how you can do those effectively.
Yeah. So really still that idea of generative model building in a sense. And
absolutely. Exactly. Yes.
Yeah. And also that mindset of like becoming okay with not knowing everything and failing and doubting and things like that, I think is extremely important. That's actually something I really learned when I started learning how to program, how to code, because, so I don't know how it works in the US, for instance, but in France, the educational system is really built around not failing. It's like the first failure that you have will make you off track, and then it's going to be extremely complicated to get back to like the, royal track, which is like what everybody wants to do, like the equivalent of the Ivy League in the US, if you want. It's like there is some...
The grand écoles, right?
Exactly. Yeah. I'm surprised you know that term, but yeah, I grew up that kind of stuff like called the Grand École, which is, that's the Ivy League, basically. And it's extremely hard to get in there. And there is just one way to get in there. Now they start to diversify that a bit, which is good. But at my time, because I'm very old, there was one main track to go there, and one mistake would make you out of that. So you become extremely good at avoiding mistakes. And, at really applying what you're supposed to do and do what you're supposed to do, which in a way is good, but at some point it becomes problematic. And so something that I really learned really when I started programming was this idea of failing all the time and becoming comfortable with, well, it's okay. I don't know how to solve that yet. I'll understand, but right now I don't know how to do that. And the fact that that line of code doesn't work, it's okay. It doesn't mean my computer is going to explode or that my career is done, And that I think is extremely important to teach students, not only as a skill, but as a mindset, because it also improves your grit, improves your determination, improves your confidence. And I think also that's why this kind of teaching not only stats, but the programming, also it teaches you the scientific method, right? It's like I have a hypothesis about that. I'm going to test it. If it doesn't work, I'm going to change my prior. And I really love that because not only teaches you skills, but also, as you were saying, a very important mindset that you can use then in other areas of your life.
Yeah, I especially like that latter point you made. And so I had mentioned that about identifiability issues, which means, okay, your model's, there's no reason to assume to think that your model has, failed. If you have identifiability issues, it's just that you need a different assay, you need a different experiment to test it, to get those parameters. But on the other side, there's what you mentioned, which is what happens if we start failing our posterior predictive checks? What this does is that actually raises the next scientific question. It shows you where your holes in your knowledge are. Now you need to figure that out, either by kind of reassessing your theory and thinking carefully about some theoretical considerations, thinking carefully about what the next experiment is to see why it's doing that. And so, yeah, I think one of the things that I ask students is I say, it's your job as a scientist to verify hypotheses, and it's not. It's to assault them, and that's where you find out new things. So yeah, that's good. Yeah, and with respect to failure, by failure, I don't. The word has such a negative connotation to it, but when you start doing statistical inference, you're gonna mess up, and there's gonna be stuff that's just hard. I mean, and that it does require you to keep trying, and you learn along the way. And I have definitely encountered plenty of student frustration. Of course, they don't often understand that I've had the same frustrations myself. That's how you learn, right?
Yeah, exactly. So I want to be, time is flying by, and I want to be conscious of your time. So
yeah, I talk too much. I'm sorry about that.
No, that's very good, actually. I always, people who talk a lot should be on podcasts. Look at me. Why do you think I have a podcast?
I suppose.
Just I cheat because I'm on each episode, so.
I see, yes, okay.
That's how much I talk. So before closing up the show with the two traditional questions, there is one other question about education that I'd like to ask you is, so we talked about the skills and so on, and we just talked about you're going to mess up when you start learning. Actually, do you think that there are mistakes that students have to make in order to really understand some statistical concepts? And if yes, which one?
I use a phrase when you wander down a dark alley, it's leading you to nowhere, but you actually gain some life experience, and you know how to avoid those dark alleys. So one of the things I think that they need to do is they need to mess up things to understand that statistical inference is fragile, that these techniques are fragile or brittle, and they break. And so I give them little problems where I know they're going to hit something that's gnarly, that's going to highlight how subtle and dastardly these problems can be. And so,
these are good.
Yeah. So for the microtubule problem, it turns out that if you do that model I told you where you work out the number of, let's say I have 3 steps. Actually, the example I give them is 2. Say it takes 2 Poisson processes to arrive for catastrophe to happen, and they can arrive, and they're different Poisson processes, so they have different rates. Okay. If you have an uninformative prior on the rates, or you have a prior that's the same for the 2 different rates, which you actually wouldn't do because you'd have to be careful too. You'd have to order them because there's a label switching identifiability issue there. But let's say that, so that gets them already, the label switching. But anyway, let's say you have not like totally uniform priors on those things. And you're going to compute a maximum a posteriori probability estimate for the parameters. They'll always have the same rate for the map every time. And you can work that out analytically, actually. In fact, you can do that with pen and paper. You can work it out. You know, they often immediately resort to numerics. And so then they're going to start to report them. They're going to be like, oh, yeah, it's one of them is 0.0451, and the other one's 0.0452 because there's some numerical, right? You know, when they think, oh, they're very close, but they're slightly different. And so that's a mistake right there that I have them intentionally fall into. And it exposes a problem with only reporting basically the mode of the posterior, right? And so what I do is I do kind of like, I don't know, it sounds mean, but I sort of set these little traps for them to like bump into to discover themselves, you know? And so I wouldn't say there's any really one mistake. It's the general idea that this whole process is brittle and that it's very easy to break and to break subtly. And so I want them to keep making all these little mistakes, and so that at the end, they're very careful and that they also don't overstate their results, because there's often subtleties that we don't know about that are lurking. And, you know, I was using a data set, I forget all the details, but I was using a data set for 4 years. And finally I had a TA notice one of those little subtle details that I had missed for years. And, you know, and I share that story with the students too. I'm like, look, like I'm no dummy, you know, it's like, I'm careful, but you're still going to get nailed. It's going to happen. And so you just got to remember that this is a precarious endeavor that you're embarking on here to do this statistical inference.
Yeah, I love that. And I do that also in my teaching, the workshops, for instance, that we do for with PyMC Labs. Often, like, especially when I teach priors in relation to generalized linear models, since you have the link functions, choosing priors is way less intuitive because of the link function. And so often I start with a somewhat classic prior, you know, normal sigma equals 10, which a lot of people just use like that. And then you look at the prior predictive checks and it looks awful. And there's just those little things, but like making the mistake will be much more powerful than the students, and they will remember that way more. Or like for the Poisson regression, for instance, like writing the model, but omitting the exponential link. And so the model won't sample because it will start around 0, and that means minus infinity probability. So PyMC won't even start sampling, which is very dreaded error when you start learning Bayesian statistics. So I do that on purpose, and then the students are like, I ask them, so what's the problem here? Our model is good, right? So what do you think is happening? So yeah, it sounds mean, and I mean, we are smiling. If the people don't see us, but we are smiling, so yeah, that's not good. But I think it's a way better way to teach people instead of just telling them, oh yeah, here, use the exponential link.
Absolutely. It can't be prescriptive. That goes back to my earliest point, which is you do not want to teach a prescription. They need to think about it, and it has to be bespoke modeling. And that takes effort, and it takes training, and it takes patience, and it takes collaboration. It actually takes all the things that we value as virtues in scientists, and we should embrace it.
Yeah. And I particularly like that part also about collaboration. Lately, I just read a book called The Illusion of Knowledge, and that's by Stephen Sloman. Yeah, The Illusion of Knowledge, Why We Never Think Alone. A really good book. I'll put that in the show notes. And yeah, it's a book basically about the strength of Homo sapiens is to collaborate. And like, basically, everything you think you know, actually, you know it because like we all know it. It's a community of knowledge. And like, basically, nobody is just on his island doing his thing. And I love that idea. It's really, really a good book. And you can find that especially in the open source community, for instance. Where it's like everybody like resting on the shoulders of giants all the time.
Doesn't that make us all giants?
I think so. Which is like
all right.
Really big shoulders.
Yeah, that's right.
Yeah, awesome. Well, Justin, I still have so many questions, but I think we have to call it a show. And before that, though, I'll ask you the two traditional questions I ask everyone at the end of the show. So first one is, if you had unlimited time and resources, which problem would you try to solve?
That's a good question, of course. For me, again, my mission is about training scientists. And I think the problem I would try to solve is the same problem that I mentioned before, which is I want to break the habit of looking for prescriptive ways of doing things with statistical inference. To me, that's a problem. And ways to solving it is by education. If you're asking more generally, I would say climate change, but I think pretty much everyone would. So, but yeah.
One of the most common answers for sure. But I'm not surprised by your answer. That's for sure. Cool. And so second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
So that's a interesting question. And I was thinking about it, and I have opinions for different reasons, but for the purposes of this podcast, I'll actually say David Mackay. And I wonder if anybody has ever said him before, but I say him because in the early reading that I was doing about these things, his book was really useful to me. The title of the book is Information Theory, Inference, and Learning Algorithms. And it's a book from like 2003 where he really brought those three topics under the same umbrella, which is really featured centrally in that is Bayesian probability. And it's written in such a clear, pedagogical, and actually even humorous at points way. And so I highlight that book because I think it's really useful for learning about these ideas. And yeah, some of the stuff is dated because it's about 20 years old now, certainly on the machine learning side of things. But the ideas and the unifying ideas of having those three areas, information theory, machine learning, and statistical inference, all kind of linked by the same ideas, is really important. Now, I mention him because his second book that he published is related to the first question, which is called Sustainable Energy Without All the Hot Air. And in that book, he uses all order of magnitude types of estimates to try to figure out how do we solve this, basically the energy problem. Again, argued with this sharp, witty, direct, engaging, fun way. And I just think that if I had the chance to sit with him, I would be intrigued, entertained, inspired. And I think that he was just really also a great scientific communicator and thinker. He died tragically at a very young age from cancer. I think he was 48 when he passed away, probably 5 or 6 years ago. But anyway, for the listeners of the podcast, both those books are fantastic. One's really probably going to help you think about Bayesian inference. The other one about one of the greatest technical challenges of our time.
Yeah. So I did the one about renewable energy to the show notes. I don't remember the name of the first one. Can you remind me?
It's called Information Theory, Inference, and Learning Algorithms. It's one of the early books that I was reading when I was getting into this area.
Yeah. Okay. Yeah, I have it. This is added to the show notes, people. Awesome. Well, Justin, thanks a lot for taking the time. I wanted to talk about sports analytics because I discovered that you're very passionate about football and you're even a goalkeeper and you were playing yesterday, and people will have heard in the introduction you did some exploits yesterday that are related in the introduction to this show. So well done. And I'm sure all listeners will join me in congratulating you.
Thank you.
Yeah. And it's not every day that a goalkeeper scores a goal, so well done.
That's true.
I hope you celebrated that as was required with the team.
I did.
Okay.
Although it was a little overshadowed because my teammate scored 4 goals right after I did that. So
come on, don't steal the goalkeeper's thunder. That's not cool.
That's right. Yeah.
That's not cool at all. Well, that will be for our next episode. And as usual, I'll put resources and a link to your website in the show notes for those who want to dig deeper, especially your courses. You have 2 courses that are particularly relevant for the listeners. So these are in the show notes. Thank you again, Justin, for taking the time and being on this show.
My pleasure. Thanks so much for having me.
You bet. And you're welcome for our next episode dedicated about goalkeepers, football, and mainly PSG.
Oh boy. Okay. We'll talk later about that.
Perfect. Okay.
All right.
See you, Justin.
All right. Bye-bye.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.